Hello everyone. So we are going to solve this problem related to the mass attached to a spring. So let's say this is a spring and we have a mass attached to it. Then the position of this mass is given by xt at time t, and where the positive values of x represents the position below the equilibrium position. So first of all, we will understand what is the equilibrium position. So when we release this mass at t is equals to 0, the mass will attain a stationary position when t tends to infinity. That stationary position of the mass is called equilibrium position. So we say that, let's say we release this mass at t is equals to 0 and it becomes stationary as t tends to infinity here. Then we say that this is where x equals to 0, and the positive values of x, if x is 2, the positive values of x tells us we are 2 unit down the equilibrium position, and negative value of x tells us that we are 1 unit above the equilibrium position. So now we have understood that. So let's read the question. If the ODE model of the position is given by this, then list all of the times mass passes through equilibrium going up. So first of all, we have to solve this differential equation. Only then we can know about the position of the mass, because the x will tell us the position of the mass and how the mass is moving. Only then we can answer this question. So let's try to solve this differential equation. So the auxiliary equation of this differential equation will be given by m square plus 20m plus 200 is equals to 0. When we find the roots, we will get minus 10 plus minus 10 iota. So you can easily find the roots of this equation by using the formula minus b plus minus under root b square divided by 2a. So after finding the roots of this quadratic equation, we have two roots, and when we have two complex roots, the solution of the differential equation is given by solution of the homogeneous differential equation is given by x of t is equals to e power minus 10t c1 cos 10t plus c2 sin 10t. Now to find the values of this coefficient c1 and c2, we will use the given initial conditions. So if you put t is equals to 0 here, then this will be 2, and if I put 0, then it will be 1, it will also be 1, so it will be c1, and this will be 0 because sine 0 is 0. So we will get c1 is equals to 2. So we can simply put c1 is equals to 2 here. Now we want to use this condition, that's why we have to take the derivative of this function. So if we take derivative, then we can put this as it is and take the derivative of this term. It will be minus 20 sine 10t plus 10 c2 cos 10t, and then we can take the derivative of this term. It will be minus 10 e power 10t into this term as it is 2 cos 10t plus c2 sin 10t. Okay, now if we put t is equals to 0, then this term will be 0, and if I put 0 here, it will be 1, it will be 0, it will be 1, it will be 0. So only remaining terms are 10 c2, okay, and minus 10, sorry, it will be 20, because if I multiply it inside, it will be 20, and that's it, because cos 0 is 1. So we will have this, and from here we can calculate c2 is equals to 2. So c1 and c2 are both equals to 2. So now we have the solution. So we can simply put c1 and c2 equals to 2. Now we have to tell, list all of the times the mass passes through equilibrium going up. So let's say if we release the mass, then it can pass the equilibrium from coming down, or it can pass by going up. Okay, so we only want to collect the times value of the t where it passes the equilibrium while going up. So when the mass is going up, the value of the uh, derivative, the value of the x will decrease. Okay, so if mass is going up, the value of x is decreasing, because the positive values of x represent the position below the equilibrium position. That's why. And when mass coming down, then the value of x is increasing. So if we look at the graph of this function, so if we start at 0, when t is 0, the x is 2, so we are starting from here. Okay, we are starting from here, and so we are starting at x equals to 2. And what does x equals to 2 means? X equals to 2 means we are starting 2 units below the equilibrium point. We are starting here. Now when we release this mass, it will go up, because it will go towards the equilibrium point. So when it goes up, the value of x will decrease, and the graph of this function will look like this, because this will decrease the amplitude as t tends to infinity. Because if t increases, this will be smaller and smaller, and these terms will cause the oscillations, but the amplitude of the oscillations will become smaller and smaller as t tends to infinity. Now we want to tell the values of t when graph passes through x equals to 0, when the mass is going up. So if let's say if we talk about this point, okay, if we talk about this point, now at this point the value of x is decreasing, the value of x is decreasing. That means the mass is going up, and at this point the value of x is increasing. That means at this point mass was coming down. So we want to collect this point, but we do not want to collect this point. So because we only want to collect points where the mass passes through equilibrium when going up. Okay, so similarly we want to collect this point, but we do not want to collect this point. Okay, all right. So so basically we want to collect the zeros of this function. So if you put this function equals to 0, then what will happen? Since this cannot be 0, so what will happen? This term will be 0. That means 2 sine 10t will be equals to minus 2 cos 10t. Then it will get cancelled. So we'll have this, and we'll have 10t is equals to minus 1. Okay, so 10t will be 10 inverse minus 1, and from here we can say that t or 10t is equals to, for the various values of t, we can add n pi here, where n is n integer, and n will take only those values for which t is positive. So let's say from here we have t is equals to 10 inverse 1, 10 inverse minus 1 plus n pi divided by 10. So this is the value of t's where the x becomes 0. But we want what do we want? We want only those values where x is decreasing. We do not want this value, we do not want this value. Okay, so to do that, wait a minute. So to do that, we have to look at the derivative, or we do not derivative. We can tell if the function is at what point the function is decreasing, and at what point function was increasing. So let's say if you put n equals to 0, then what will happen? Then t will become negative. We are not interested in that because we want our time to be positive. So if you put t is equals to, if you put n equals to 1, then we will have t is equals to tan inverse minus 1 plus pi by 10. And what is tan inverse minus 1? We can take the principal value of tan inverse minus 1, which is minus tan inverse 1, and tan inverse 1 is pi by 4, so minus pi by 4. So that will be the first equilibrium point, let's say first time when x is equals to 0. And here we can from the graph we can clearly see that here the x was decreasing, so the mass was going up. So that means this is the point we want to collect. But if you put n is equals to 2, then we will get this point. But we do not want to collect this point because at this point the x was decreasing and mass was coming down. So we only want to collect all those t's of such kind when n is equals to 1, 3, 5, 7 and so on. So the collection of all those points will be t is equals to, so we can take it as minus pi by 4 plus n pi divided by 10, such that n is equals to 1, 3, 5, 7, 9 and so on. So this is the collection of all those points when or when mass passes equilibrium point by going up. Okay, so we can write it in the set form. Let's say if we want to write it in the set form, then the set will be, let's say we denote that set by a, capital A, then that set of points will be minus pi by 4 plus n pi by 10, such that n is equals to 1, 3, 5 and 7. So that will be a set of all those points where mass passes equilibrium by going up. Okay, so that's it for this video and thank you for watching.